A single 200 megawatt data center consumes enough power to run a small city. This demand is concentrated into one campus, creating a massive energy vacuum. Cooling these systems evaporates 5 million gallons of water daily, raising temperatures by 7 degrees Celsius within a 3-mile radius. These chimneys create a thermal convergence zone where powerful updrafts pierce the boundary layer, generating thunderstorms, large hail, and localized flooding. The current straight-line consumption model, pulling massive grid power just to eject 60-degree wastewater, is a physical bottleneck. This energy waste creates an operational limit that caps the future growth of AI infrastructure. Recursive energy closes this loop by treating a facility's waste heat as the primary fuel source for a secondary refinery. By using heat to generate electricity, the system sustains its own input. The process begins with 60 degrees Celsius wastewater. Off-the-shelf industrial heat pumps escalate this water to over 300 degrees, creating the thermal energy needed to drive steam turbine generators. These turbines generate 100 megawatts of electrical power. While 60 megawatts run the internal system controls, 17 megawatts are returned directly to the data center to offset its primary grid usage. Reliability is managed through an N+1 generator matrix, 18 active turbines, and 1 backup, supported by 100 megawatt molten sand batteries. Molten sand batteries store energy thermally in sand or graphite, providing 3 hours of emergency power for a controlled shutdown if the grid fails. By treating heat as a fuel, the data center powers its own safety architecture. This creates a self-reinforcing cycle that increases reliability without adding risk to the primary hardware. After the electrical generation phase, the system is still left with 160 megawatts of high-grade thermal energy. This heat is used as the raw energy for manufacturing vanadium redox flow batteries, or VRFBs. VRFBs are large-scale energy storage systems used for long-duration grid stabilization. Unlike traditional cooling towers that vent heat into the atmosphere, this manufacturing process sequesters the thermal energy. The heat is permanently locked into the battery electrolytes, removing it from the local environment entirely. These batteries can be stored at room temperature indefinitely and shipped across the state. They provide the physical infrastructure needed to stabilize solar and wind farms, essentially bottling data center heat for use elsewhere on the grid. Instead of paying to vent an environmental hazard, the facility now manufactures and exports high-value energy assets. This thermodynamic efficiency alters the facility's balance sheet. By recapturing waste, the system transforms a massive utility cost into a manufacturing profit center. The stability of the power grid relies entirely on physical momentum. For decades, supply and demand have been balanced by the sheer mechanical force of massive steel turbines spinning at constant speeds. When those generators grind to a halt, the network loses its physical anchor. As utilities aggressively retire heavy baseload fossil fuel plants to meet clean energy mandates, they remove thousands of tons of spinning mechanical mass from the system. This descending line chart plots the steady decline of mechanical grid inertia over the last 10 years. At the 2026 projection mark, the available spinning mass plummets, creating a severe mechanical deficit right as demand peaks. Standard chemical battery energy storage systems attempt to fill this gap using software-driven inverters. Because these modern batteries lack heavy physical mass, they cannot provide instantaneous kinetic resistance when the grid frequency drops rapidly. A modern grid powered purely by inverter-based renewables and digital battery backups is physically fragile without the integration of true physical spinning reserve. Compounding this deficit is the aggressive scaling of AI data centers, which are projected to drive unprecedented localized power demand spikes by 2026. These hyperscale compute clusters produce massive amounts of waste heat. Rather than venting this energy into the atmosphere, it functions as an untapped, highly concentrated thermodynamic asset. The engineering solution to both the data center cooling load and regional grid instability is the Recursive Energy Hub. The hub operates on a hybrid architectural philosophy. It pairs the instant electrical response of vanadium redox flow batteries with the heavy thermal mass of graphite and molten sand, all driving a mechanical turbine. By combining chemical storage with physical rotating mass, the hub repurposes traditional data center cooling infrastructure into a mechanical grid-stabilizing asset. Delivering millisecond-accurate grid response requires a precise sequence of specialized hardware components working in tandem. This isometric blueprint of the hub architecture begins with the vanadium redox flow battery module, which serves as the primary source of instantaneous inverter power. The VRFB discharges electricity with near-zero latency, immediately addressing localized voltage sags. However, the flow battery is entirely chemical. It cannot generate the mechanical resistance required to stop a severe grid frequency collapse. To address this, the design introduces a heavy graphite thermal storage block. Graphite possesses excellent thermal conductivity, allowing it to capture intense heat rapidly and provide sub-cycle kinetic response during sudden demand events. The system then layers in deep reserves of molten sand. Molten sand offers a sustained, high-capacity thermal profile, allowing the hub to store vast amounts of heat for hours without significant dissipation. Finally, the turbine generator architecture is added to the blueprint, serving as the physical plant's heavy spinning reserve. Energy transfers from solid and liquid thermal blocks into the turbine via direct mechanical coupling, forcing heavy blades to rotate at grid-synchronized speeds. Waste heat from AI server racks travels along specific pathways, charging the graphite and sand mediums. Simultaneous integrated electrical pathways connect both the flow battery and the physical turbine directly to the external distribution substation. When a sudden grid frequency drop occurs, the system triggers a coordinated physical pushback. As the grid sags, it effectively attempts to slow the turbine down. The heavy blades push back, maintaining rotational velocity against massive physical resistance. This sustained physical momentum injects true inertial response straight into the power network, mechanically bracing the grid against collapse. Holding the frequency steady, the hub buys the critical millisecond buffer that traditional peaking plants require to spin up and bring the network back to baseline. Applying this internal architecture to a full-scale 200-megawatt AI data center yields highly specific thermodynamic efficiencies. This Sankey diagram isolates the energy flow for a standard 200-megawatt data center, exposing the 40-megawatt parasitic load dedicated entirely to standard cooling chillers. Integrating the hub architecture physically replaces and completely eliminates the requirement for these traditional chilling units. As a result, that 40-megawatt quote drops off the facility's input flow entirely. The raw waste heat generated by the AI compute clusters is now rerouted directly into the hub's graphite and molten sand thermal blocks. Through the mechanical coupling we established earlier, the captured heat drives the turbines, executing a strict thermodynamic conversion back into usable electricity. This newly generated power flows from the thermal conversion blocks back into the data center's primary operational grid. This process returns exactly 17 megawatts of reclaimed electrical power. Combining the 40-megawatt cooling reduction with the 17 megawatts returned establishes a total energy delta of 57 megawatts. A 57-megawatt offset is the equivalent output of a mid-sized municipal power plant, now entirely removed from the local utility's responsibility. During peak summer stress events, removing this massive draw from the local grid significantly reduces the risk of rolling blackouts for the surrounding region. Thermodynamically re-engineering the cooling loop converts the data center's largest energy liability into a self-sustaining utility offset. In addition to internal offsets, the hub is equipped with 100 megawatts of thermal reserves, acting as a capacity engine for external grid operations. This deep reserve lets the facility execute a triad of grid support for regional energy management. This three-panel timeline graph plots the system's operational flexibility. The first panel defines Mode 1, grid peaking, managing discharge curves during high-demand hours. During peak grid stress, the hub discharges its reserves to the turbines, effectively zeroing out the data center's utility draw, and frequently exporting surplus power straight to the local substation. Shifting to the second panel, the system shifts timelines to define Mode 2, black startup, or island mode. If the regional power grid experiences a catastrophic collapse, the facility immediately severs its connection to the utility. In Phase 1 of island mode, the VRFB and graphite reserves deploy instantly, providing sub-cycle electrical and thermal stabilization to catch the massive computing load. Phase 2 follows seamlessly, as molten sand reserves take over turbine drive operations, keeping AI clusters online without interruption. The The third panel illustrates Mode 3, emergency support, utilizing the system's ability to maintain high-intensity discharge over a 1 to 3 hour duration. These short-duration discharge capabilities allow the data center to act as a community security blanket, bridging the power gap during transformer failures or unexpected transmission maintenance. Looking at this macro-level grid map, the technology expands to address bottlenecks at congested nodes, particularly distribution substations tied to solar and wind farms. Siting hubs at these high-traffic intersections deploys 100 megawatts of storage exactly where transmission lines are weakest. Capturing and holding renewable energy at the source prevents local substation transformers from overloading during peak afternoon generation periods. The map also highlights legacy generation plants. Retrofitting these aging facilities with integrated thermal energy storage systems entirely changes their operational profile. Mechanically, the retrofit directly intercepts the substantial cooling losses native to traditional steam plants, heat usually vented into the atmosphere, and sequesters it directly into the hub's thermal mediums for regeneration through the turbine generator. By reclaiming these previously unrecoverable losses, the hub can extend the operational life of legacy plants while raising their total thermodynamic efficiency by up to 12%. Scaling this hybrid infrastructure requires meeting strict financial and regulatory prerequisites. Local utilities pay millions in frequency regulation contracts, but continuously qualifying for these payments demands precise, proven technological performance. Developers must utilize standardized, rigorously tested hardware to guarantee continuous compliance with complex FERC mandates regarding grid interaction. This formal technical audit document details the required compliance data, capturing the strict 10% commodity and energy royalty demands. This chart compares the return on investment. While standard data centers typically see a payback period of 5 to 10 years, the Recursive model reduces that timeline to 15 to 18 months. We are currently opening 5 non-exclusive partnership slots for developers ready to set the standard for this closed-loop model. The $10 million annual licensing fee is a net zero cost. As this balance sheet shows, the fee is fully offset by the immediate reduction in electrical and water expenses from day one. Adopting the Recursive model transitions you from a cost center to a net profit energy asset. Find full specifications and licensing details at techgeniemedia.co.